This lecture is an introduction to uncertainty. Uncertainty is very important in climate science, it's very important in decision making. It is something that is a barrier. It can be a barrier in fact because we need more information and to improve the certainty about the conclusions that we're making. However, in most cases, one could say it's a barrier because of how people choose to use it and how people choose to especially make a statement about we cannot make a decision because it's so uncertain. In that statement, there's frequently a lot of politics, and if you look for the evidence to support that statement, you will often find that it is unsupported by evidence. In the early lectures of the course on the scientific method, it was stated that scientific research produces knowledge with a description of the uncertainty associated with that knowledge. The word description was very deliberately chosen to distinguish it from the quantification of the uncertainty associated with that knowledge, because in many cases the quantification is at best only part of the description, and in many cases the quantification is not in fact very meaningful. It is important to me to restate that science and scientific research does not in general produce facts. I think this is important because many students learn science as a list of facts, and science does not produce facts. Again, it produces knowledge with a description of uncertainty. If there are facts, and they would be very rare, then facts might be defined as knowledge that has uncertainty that is vanishingly small or close to zero. Again, facts are certain, but facts are rare. And as part of communication, I recommend to my students not to call science the facts. Do not say, we have scientific proof, we have the scientific facts, because especially in the scientific investigation of a complex system such as climate change, one very rarely has something that one can call a fact. Here are some simple examples of uncertainty. All of these involve temperature. One of them would be, in my science class, I measured the temperature that water boils at, and it came out to be 212 degrees Fahrenheit plus or minus 1 degree. Another temperature example, tomorrow the high temperature will be 43 degrees Fahrenheit plus or minus 2 degrees. The high temperature tomorrow will be between 41 and 45 degrees. In all of these cases, a number has been provided for the temperature, 212 or 43, and a number has been provided to give some sort of estimate of the uncertainty associated with that number. The number that is quoted as the uncertainty or the error is, in the case of the experiment of the boiling water, perhaps simply related to one's ability to read the scale on a thermometer. There would also, in that case, be what is the model that we use to determine when something's boiling? How do I decide that something is boiling? Is it when I see little bubbles, big bubbles, a rolling boil, a simmer? When we go into a problem like that, there are many, many sources of uncertainty. The temperature predictions for the second two bullets there, the 43 degrees, either is plus or minus 2 or range from 41 to 45, is likely based upon a professional weather forecaster's estimate based upon experience. That is, that normally in a weather situation such as this, we can generally get the temperature to within plus or minus 1 or 2 degrees. Uncertainty is complicated, though. There are many reasons that our knowledge might be imperfect, And in fact, one can just think of uncertainty measurement, uncertainty description as a description of the imperfection of our knowledge. Some parts of it might be random. It might be hard to measure. There might be things that we just simply do not know. We might have some things that are simply difficult to describe. And we might have things that are difficult to model. And if we can't model it, then I would say that we do not actually have a very good idea of the processes that are involved in determining the behavior of a particular phenomenon. These 5 bullets that I put here are really just a high-level description of places we might have uncertainty. And even as we go through the rest of this talk, you'll see different ways that different people think about and parse the uncertainty, with a particular emphasis in this case on climate change, and climate projections. Academics and philosophers have studied uncertainty for ages. It would be one of the oldest subjects of philosophy. And often in an introduction, they would have 2 categories: the aleatory uncertainty, which is dependent upon chance, randomness, and something that is ultimately irreducible. An example for that is the flipping of a coin. You might be able to develop very good statistics for that, but you are uncertain in every flip of the coin of whether it will be heads or tails. The other type of uncertainty that's frequently defined in these 2 categories is called epistemic, or truth. What is the truth? These are knowledge-based. You're looking at something that could be knowable. And in this case, this would be a situation where gathering more knowledge might reduce the uncertainty. However, that reduction of uncertainty may or may not have been providing a barrier in your ability to use that knowledge. I'm also going to add these other 2 things that have started to emerge from artificial intelligence. And the idea, if you're working in artificial intelligence and you get a result that might be reduced to some propositions, what do those propositions actually mean? What do they mean in terms of mapping that over to the real world? And then another one, this type of uncertainty that's called ontological uncertainty, again coming from an artificial intelligence approach. One of the things that's implicit in artificial intelligence that you're going to be able to model the future based upon the past. And what if the future is really much different from the past? And this gets us to the ideas such as what are the unknown unknowns, and the fact that there are always things that may just, let's say, pop out of the blue that we are presently have not experienced and are unaware of. I'm going to start with observational uncertainty. One of the reasons I'm going to do this is that observational uncertainty is very foundational to science. Science is based on observations, and observations are uncertain. Another reason that I like to start with observational uncertainty is that in the discussion of uncertainty and climate change, we often move very quickly to the uncertainties that are associated with models and forget at some level that there are observational uncertainties. There are some things that we have not observed adequately enough to be able to describe them, and some of those things are really quite important. And observational uncertainty can come from a lack of data, an inadequate or incomplete measurement, which might come from not being able to measure things adequately to sample the environment that we're measuring. Statistical variation arising from measurement instruments and methods. Systematic error in our ability to measure a particular quantity. Subjective judgments needed to estimate what you're seeing in the observations and your interpretation there. And then, of course, there is the inherent randomness of a system and of an observation. It is important to realize that from a philosophical point of view, that the climate, the Earth, can never be observed with certainty. We just can't measure everything everywhere all the time. Therefore, we're always relying upon sampling. We're always relying upon the development of statistics and the arguments that our measurements are, in fact, representative of what is going on. And in other lectures, I talk about the uncertainty, let's say, associated with the surface temperature observations. And you can see in the lecture that actually is scheduled to follow this one, if one were to go sequentially through these, that over time, as the observing system has increased, the uncertainty about our estimate of the global temperature is really very, very small. If we look into what is presently a common framework for thinking about climate uncertainty, we come down to really people starting to think more and more, what is the uncertainty of what we're saying about the future? And in that case, we often end up with these three types of uncertainty, something that's called the scenario uncertainty. For example, how much carbon dioxide will we emit in the future? This depends on things such as how many people there are, what sort of policies we have. And of course, it's not just carbon dioxide. It also has land use change and other greenhouse gases. There's a version of this that I would like to say comes from looking at the past. If we're going to investigate the past, for example, what caused the Little Ice Age or the variability of the 20th century, we need to be able to specify what we would call the radiative forcing. And I refer students to the lectures on radiative forcing if you need to know what that term means. And in that case, for example, we would need to know what the aerosols are. And as you know from the aerosol lectures, aerosols are very complex because they're short-lived, they are regional in nature, and their composition is important. We have very limited ability to determine that forcing. That sort of forcing, when we look at the past, is often wrapped up in something called, say, the boundary conditions or the specifications that are provided to the model. There's another class of model uncertainty that is the weaknesses of the model to represent the physical, chemical, and biological processes. And I'm going to have in the next slide a little more detail on model uncertainty, so I'm not going to belabor the point here. And then the third in this framework of uncertainty is what we call internal variability, the variability of the climate that's not caused by human-made changes. That would be the variability that might be associated with the ocean-atmosphere interaction that we know as El Niño. It would be the variability that comes from volcanic eruptions. Sometimes this variability is called natural variability, but I think it's a better term to call it internal variability, even though I recognize that that's a pretty abstract notion of this idea of a system and different parts of the system varying together, that there's some relationship, again, as an example, between the atmosphere and the ocean and the exchange of heat and even carbon dioxide on time scales, say, associated with El Niño. And there are many other sources of variability that we will detail in a lecture on that subject. In an earlier view graph, I talked in a little more detail about the type of uncertainties that might be of interest to an expert in observational uncertainty. Here are some types of uncertainty that would be of interest to somebody who's building predictive models. What are the boundary conditions? A simple one would be, how well do we represent the mountains on the planet? If you think of a climate model that is resolving things at, say, 5 degrees latitude versus one that's resolving things at a half a degree latitude, the representation of the mountains will be very different in those to model simulations. And even at a half a degree, anyone who's been in the mountains knows that there's a lot of variability that is occurring on smaller scales. It's going to be incredibly important in regional climate problems. Their initial conditions. Some problems are very reliant upon how well do we know the state of the climate, know the state of the atmosphere, the ocean, and the land and the ice when we start a simulation. This is very important for short-term planning, for example, on a year, 2 years, because of the variability associated with the ocean. Frequently, in a short local problem, the initial conditions have an immense effect on the uncertainty. There's the structural formulation of the physics, which I will discuss more in an example in the end, but the most daunting one of those is how well are clouds and how well are the dynamics that are responsible for the formation of clouds, how well are they represented in the models. There's parametric uncertainty. If we were to have a reasonably robust model to represent a process that's dependent upon a number of parameters, how well do we know those parameters? There's the numerical formulation. We have equations that are continuous, and even they are an imperfect representation of the science, but we can't solve those equations, so we make numerical estimates using computers. How well do we do that numerical formulation? And then we also frequently, in our efforts to apply models, after we have a model that is, say, at a 2-degree spatial resolution, 2 degrees of latitude, that is, but we need information on a smaller scale. How do we tailor that information through something called downscaling? How do we deal with noise through the development of derived products that we need to actually use the information coming out of the models? I think this is interesting enough to take up the time of a slide, which is another way you might think about uncertainty associated with climate science. And this comes from a document called A National Strategy for Advancing Climate Modeling. It talked about value uncertainty in data such as observations. So that's very similar to what we saw earlier in terms of observational uncertainty. Structural uncertainty, an incomplete understanding of processes or how to model them, so that would be in the realm of model uncertainty. But in this description, this idea of predictability, or really unpredictability, that there are fundamental limitations to the ability to predict something. And this is the idea that there are certain characteristics of a fluid that make it hard to predict in a deterministic way for longer than some characteristic amount of time, depending upon the problem that you have. And after that, you can predict it in a probabilistic way, but the system has a character that's sometimes called chaos, in the sense that the details of the fluid flow, the actual waves, the actual vortices that are going to be transporting the heat, energy, momentum, and mass within the fluid, the details of that cannot be predicted, but we do have the ability in a probabilistic or statistical way to represent the fluid. So this is a different parsing, I'll say, a different way to slice through uncertainty. And any of these things that are getting these things down to 2 or 3 classifications or types are going to be subject to being incomplete. And therefore, all of these things are frameworks to help investigators in their quest to look at particular types of problems. Another thing I'll mention about uncertainty, which I think is actually quite interesting, especially when we think about the practice of science and the communication of uncertainty, is controversy and consistency. Do we have conflicting information and controversy about phenomena? Do we have different ways to explain the phenomena? Then another one is, are results changing in a fundamental way from one study or one assessment, such as we do in climate, from one assessment to the next? Do we do things that are credible in their approach, and the different approaches give us very different results? If we are in that situation, that tells us there's something fundamentally incorrect about some aspect of our scientific investigation. And one of the purposes of, again, another lecture in the series on uncertainty, the ones that are looking at IPCC temperature, one of the points that's made in there that over 5-year periods, we do not see major qualitative differences in the outcomes of the predictions of warming. One of the things that gives us confidence in those results is that, going to the last bullet on this slide, there is physical consistency between the theory, say the conservation of energy, observations, and simulation. And when all of these things align together, when there is consistency, when scientists who are coming at it from different directions start to converge on the same explanation, there is a certain confidence that comes from that process. Then finally, there's the communication of uncertainty. If I tell you that something is highly likely, or a word that was used by the IPCC, unequivocal, what does that really mean? Highly likely means different things to different people. Highly likely means different things depending upon the problem that you're working on. So what do the words mean? How do people interpret uncertainty? One of the things that I think is most important and critical to this course is climate uncertainty in the context with other uncertainty. When looking at real-world problems that have engineering and policy and finance, climate uncertainty is very rarely the biggest uncertainty. And in almost all cases, we've been dealing with weather uncertainty, and so climate uncertainty is something of a modification of how we've been dealing with weather uncertainty. That doesn't mean that it's easy, but it means that in a problem-solving environment, it's probably not the place that you should be most concerned about how certain you are about good and bad outcomes in moving forward and taking some action. And I started at the top, what do words mean? I end at the bottom, what do numbers mean? Sometimes scientists will go out of their way to provide a number on something that is fundamentally very uncertain. And there's, in fact, research that shows that this specification, perhaps overspecification of numbers to describe uncertainty, does not increase the usability of climate information by practitioners. I want to end with an example, and it's a pretty complex example. I want to go back to the clouds, aerosols, and the feedbacks. And from the lectures on feedbacks, changes to clouds can heat or cool the Earth, and they require careful quantitative evaluation. For example, there's a lot of complexity in clouds, and more high clouds are likely to heat the surface, and more low clouds are likely to cool the surface. And then we introduce aerosols, these particles, and they can have a direct effect, and depending upon their composition and color, that they might heat, they might cool. But to make it even more complicated, they have indirect effects because they change clouds. And they can change clouds from whether they heat or from whether they cool, depending upon, say, how they change the droplet size in clouds. And in those lectures, I went through in some detail figures that looked like this. So in the clouds, we had this idea of reflection, we have this idea of absorption. So more clouds generally mean more reflection of solar, which would be a cooling effect. More clouds mean more infrared to the surface, which would be a warming effect. We have water vapor feedback. So there's a lot of uncertainty associated with clouds. Then we introduce aerosols, which have issues of size, issues of composition. They are not spatially evenly distributed. They don't last in the atmosphere that long, but they're always being stirred up and put into the atmosphere. They can mean more reflection. They can mean more absorption. So they can heat or they can cool. And then we have, again, this idea of aerosols interacting with clouds, which can change their cloud height. They can change cloud reflectivity. They can change the ability of a cloud to rain. And remember that rain is, from a climate scientist perspective, rain is energy because of the phase transition of water. And then they can change the size of the droplets, so they can change the radiative characteristics of clouds. Then I have this figure. The point I want to make is that these cloud microphysical processes, which occur on scales of micrometers, micrometers, 10 to the minus 6 meters, and can occur on time scales of minutes, perhaps even seconds, they have an incredible influence on the formation of droplets, water droplets, which can either remain in the air or fall out if they get heavy enough. These processes that are on these very small scales have important influence on the reflection and the absorption for the entire planet. Therefore, there is this link across spatial and temporal scales that is very difficult to represent quantitatively, robustly, and accurately. And if you were to look at what's going on within the field, you will see that decisions that are made about cloud microphysics can completely alter the feedback that clouds might have and how much they warm or how much they cool. Therefore, one has to look at other strategies and other sources of information in order to be able to answer and constrain the type of problems in any fundamental ways. So the point here is really this enormous variety of scales. By scales, I mean the characteristic spatial sizes and the characteristic time spans on which processes occur, and how processes that occur on small and fast scales have very important influences on large and slow scales. And this interaction across scales is very difficult to define with high certainty. So what are the challenges in that type of problem? We have problems of how well can we measure those processes? How well can we describe their behavior? Can we get enough measurements to really define the system? How well can we quantify the behavior? Can we do it statistically? Can we do it physically? Can we find consistency between the statistical and the physical representations? And then back to this idea of how well do we represent the influence of processes that occur on scales of perhaps micrometers and minutes, on global scales that are years to centuries. And some of these problems are so fundamental that some scientists would, I think, directly question the validity of the whole approach. And I would agree with those scientists if that was the only source of information you have. That's why you have to look at multiple strategies. That's why you have to go back to the consistency between observations, theory, and not just a model, but an entire range of models that are designed for their particular purposes, to investigate the processes, and through that investigation to describe the uncertainty that we are facing. So we are left with there are important and consequential uncertainties in climate science. There is, in fact, irreducible uncertainty. They're also, with the important societal challenges, they are all also encumbered with great uncertainty. And when we put climate uncertainty in context with those, we often find that the climate uncertainty is not what is keeping us from moving forward. When we're thinking about problem solving, a goal is how do we describe and manage uncertainty, because we need to be able to take action in the presence of uncertainty. Therefore, the problem is how do we manage uncertainty? If you are of the mindset that the uncertainty stops us from doing problems, if you're in the mindset of there's a barrier there that you cannot get around, then that places you in a very difficult static state of how are you going to address these problems. This is very, of course, troublesome if the evidence is that these are important problems to address and you feel that uncertainty has to be reduced before you can address them. And with that, I have completed an introduction to uncertainty.